Good morning. This is lesson 5.1.3 from Integrated Math 3 CPM. So I'm going to review quickly the answers to a couple of the problems within the lesson in a recording in case this is more valuable to you. The lesson objective is that I will practice how to determine the inverse of a function in different ways. One of them could be that you use a table of values where again you switch the inputs and outputs. The second method is graphically. So graphically, you could also switch the inputs, but you could also just reflect it over the line. So reflect by reflecting over the line y equals x. And algebraically is very similar to the concept of like switching x and y in your table of values, or switching your x and your y in your points. Algebraically, you would again switch x and y and then solve for y. That y is going to be your inverse function. So those are the three things that we're practicing today in this lesson. There's nothing really new. It's just intended to strengthen your understanding and build your confidence. So the first problem that you should have done would be to just, from a graph in problem 515C, switch all of the points to be able to at least graph the inverse, which would be a non-function. And at this point, we do not know how to write the equation for it. But on problem 539, they gave you a table of values, and they asked you to write the equation for the function as well as for its inverse. So in general, this is the equation of their original function. Its inverse, everything just switches. So for example, for the first coordinate pair, the input would be -5. Now going in would output a 1. For the next one, if a 7 goes in, it will output a 3. And for the next one, if a 19 goes in, it will output a 5, followed by a 31 will output a 7. So that at least takes care of writing the inverse. Now, in terms of figuring out the equation, you might have guessed what the equation is right in the beginning. If we were trying to think about would it work to say double the input and add 1, that does work for this. If we double the input and add 1. But if we double 5 and add 1, we definitely don't get to a 19. We could try, perhaps instead of doubling, tripling it, and then maybe taking away 2. So there's different things that we could try to see if it's like some type of linear function. But one of the other things, very basically, is I happen to notice that these look like that they were going up by a constant amount, right? Like I happen to see that from 7 to 19, my delta y here is adding 12, and 19 plus 12, my delta y, is also plus 12. And we're having a constant rate of change because that was as the x value was increasing by 2. So again, our delta x was adding 2. When that happens, that means that we've got a linear function, right? And when we talk about slope for a linear function, delta y over delta x, in this case, would be the 12, and that's a positive, over the positive 2. So that reduces to a slope of 6. That will enable me to write the equation that, again, it's 6x. And there are multiple ways that you could figure out the y-intercept. The y-intercept would be just 1 back from this input of 1. And for the change of 1, that change is 6 per 1. So if you thought about going back 6, that's one way to do that. And 6 back from -5 is -11. There's also another way to do that by algebraically, again, solving for your y-intercept. But this is the equation, again, of the original function. And thinking about its inverse, well, if we want, we could, of course, like try to figure out how to write its inverse by thinking about constant rate of change. We also could write in words what's happening to x, so maybe we'll try that. So x is being multiplied by 6, followed by you subtract 11. And so the inverse equation, when we think about writing it, it will be adding 11 first, followed by dividing by 6. And so if we write the inverse's equation, it would be adding 11 first and then dividing by 6. So that is the inverse's equation. If I was really thinking that I needed to graph that, I would have to simplify this to say 1/6 of x and then plus 11/6. That y-intercept would not be nice to graph, though, because it's just a little bit less than 2. It's not an integer. So that's the first problem. We found both the original function and its inverse equation. Again, the relationship between the table of values is that they just switch. For the next problem I wanted to go over again is a follow-up to that. Write the inverse for each function below. This is very similar to what we have been doing. And so if I have my original function, I could totally write this in words. And again, that's what we've been doing. But I want to try this algebraically just because that was something new that we went over in the last lesson. So I'm going to try algebraically. So this is an algebraic method. And so algebraically, we need to switch the x and the y. If you think about the original equation, f of x really is the same thing as y. So if I replace that, it makes it a lot more obvious to me that, oh, okay, algebraically, we switch the x and the y. So x equals 2 times y minus 1 cubed. And now I need to, after I switch x and y, right, we switch x and y. And now we solve or isolate y. So solve for means to isolate y. So if I do that, the first thing I would have to do is actually divide by 2 to get that y by itself. But now we still have y minus 1 cubed. In order to undo this, we would actually have to take the cube root of both sides. That undoes something cubed. And when I take the cube root of the other side, that just drops me out a y minus 1. There's no absolute value because a cube root does preserve, and so does a cube, any negative, so we don't take out the absolute value. The last step is just to solve for y. So again, y equals, when I add 1 to the other side, I have the cube root of x minus 2, and then plus 1. This is the inverse equation. Please note that this plus 1 is not underneath the square root. So that is my final inverse equation. If I did the same thing for the other one, I could again algebraically solve for the solution. I could also try doing this in words. In words, this seems like there's an awful lot of things that happen, but I'm going to go ahead and try it out. So if I talk about the original one in words, what happens to x is quite cumbersome. The first thing that happens to x is you take away 9. The second thing that happens to x is you divide by 2. The third thing that happens to the input is you multiply by 3. And the fourth thing that you do would be to add 20. To write the inverse now, so the inverse in words, again, is my strategy. 1, I would do the opposite of adding 20. I would take away 20. 2, I would do the opposite of multiplying by 3, but I would divide by 3. I would do the opposite or inverse operation to divide is multiply by 2. And finally, add 9. Now to write the inverse equation now, I have f inverse of x equaling, again, the first thing I do to x is I subtract 20. The next thing I do is to divide by 3, followed by, again, in this case, multiplying by 2. Most of the time we write multiplying in the front, so multiplying by 2, and finally adding 9. And that's how I would do writing the inverse equation using, again, the words method. I hope that these have been helpful. Please take a look at the next video for when I go over problem 5-42, which introduces the concept of the composite function. Again, here is my final equation. It was a little bit off the screen with, again, that final step of the addition of 9. So that's the answer to B. Thank you.